back to 0, and then the negative, and then you don't have all that undulating show of brightness. We don't have that alternating intensity of the brightness of the bulb as we have in AC. In DC, just comes on, attains maximum brightness, and remains that way. So that is one way of really differentiating AC voltage from a DC voltage by using the waveform, and also explaining how an incandescent bulb would respond to being powered by an AC voltage source initially, and now a DC voltage source. Now with that, we're going back to, let's go back to AC voltage. Let's go back to AC voltage. We've differentiated AC voltage from DC voltage by their waveforms and by their circuits. So the next thing we want to do now is we want to define some terms in AC voltage. AC voltage, going back to AC voltage, some terms we want to define. One of them is the RMS value. The RMS value. So RMS means it means root mean square. That is what it stands for. So V, if I say VRMS, that is the RMS voltage. Now what is the RMS voltage? Now RMS voltage is the voltage level of an AC power source or voltage source, AC voltage source that gives the same heating effect as the equivalent DC power. Now, what does this mean? It might just seem like a lengthy definition, but it's a simple explanation for that. So let's explain what VRMS means, what RMS voltage means. So RMS voltage, what does it mean? Let's draw an AC voltage source once again. Now if I have an AC voltage source of this nature, like this, and my V peak is 5 volts, positive 5 volts, and negative V peak is minus 5 volts, and something of this nature, up and down like this. And I have a DC source nearby, time, volt, time, and it's just giving me plus 5 volts. Now let's call this V1 and V2. V1 is an AC source. So if this is a voltage source V1, I connect this to, let's heating elements. This is an heating element, and I connect This is DC source V1, DC source V2, long short V2 this way to another heating element. So V1 and V2. Now, if we try to analyze the behavior of this heating element, we know what heating elements are. They are the kind of materials. They are materials that they are resistive materials too, actually. But the only difference between them and your normal resistor is that they convert electrical energy to heat. Basically, almost every joule of or almost every joule of electrical energy, that electrical power rather, that is fed to them is converted to heat. So it means that if you connect, it's the kind of material, the kind of resistive material or inductive material that you find in your electric cookers. So if you connect an heating element to a voltage source, of course it converts that electrical energy to heat energy. So you can either connect an AC voltage source to your heating element or a DC voltage source to your heating element. So as usual, since they are loads, they are resistive loads, so current will flow through them. In this case, current is flowing, since it's AC, in both directions. When it's going upwards like this, it flows initially this way. As it's increasing, the intensity of the current or the magnitude of the current increases as the voltage increases. When it gets to the peak, it reaches peak current. That's peak heat. The heat from this heating element is just like when we had the incandescent bulb connected. As the voltage is increasing, the intensity of the heat or the amount of heat energy in joules produced by the heat element is increases gradually. When it gets here at the peak, that's the peak heat energy produced. And then when the voltage starts dropping, the heat energy gradually decreases. At this point, no extra heat. The heat element is basically turned off. And then at the other, when the waveform enters the negative phase, then the direction of the current goes in the other direction. So the point is that just as the incandescent bulb was coming off, on and off, on and off, on and off, about 50 times or 50 cycles in 1 second, for the heating element, you are basically turning the heat element, you are turning it on. You are turning it on, off, on, off, on, off 50 times in a single second. Now the question is that because of the way temperature properties, it's not digital, it's analog in nature, in that just because the voltage drops from the peak back to zero, it doesn't mean that the heating element will actually be cold. When it rises, it becomes hot, and it starts dropping back to zero. The heating element doesn't just come to zero instantly. So although it's actually fluctuating, you may not actually notice the fluctuation in the temperature. Temperature it's not a digital value. It doesn't move. It doesn't vary that sharply. It's more of a gradual. It varies in magnitude gradually. So you won't actually notice the variation in the temperature with AC. If you can touch, if it's not too hot for you to touch, if you touch it, or if you connect a thermometer to your heating element, you realize that the temperature is pretty constant, although the voltage is fluctuating. On the current inside of current flowing through the heating element also be fluctuating, going in two directions, forward and back, forward and back, forward and back. The temperature is pretty much constant at a constant level. Now let's compare that with this in V2. When you connect a DC voltage source of a V peak of 5 volts to an heating element, current flows in one direction from positive terminal to the negative terminal, and it's basically fixed. So you are basically turning on the heating element, permanently turning it on. There's no fluctuation in voltage, it's just on. So if we're just logically looking at this, which one of the two heating elements do you think will be hotter over a time frame of, let's say, 2 minutes. In 2 minutes, if you measure the temperature of both heating elements, this automatically or logically should be hotter than this, because you are supplying constant voltage, constant power to the heating element. But in this case, the voltage you're supplying is alternating. You are varying it. You're turning it on and off, on and off. So effectively, you're going to have an average voltage. So you're going to have average power, basically. So this, unlike when you're supplying constant 5 volts, you're supplying positive 5 volts 0, negative 5 volts 0, and you're varying values in between those fixed points, 0, plus 5, 0, minus 5. You are varying the voltage. So the heating property, or the heat energy in joules that you derive from this will be much less than what you get from this. So that is where the RMS value comes into play. That's why sometimes, although we are applying 5 volts peak value from the AC, it's actually just it's abrupt. It's just at a single point. It's actually just 5 volts at an instant, just at this point, at this peak here. Every other time it's less than 5 volts, and you are supplying negative 5 volts only at this point. So you can't compare that to when you're applying positive 5 volts constantly. So it means that in actual fact, although you are touching 5 volts positive and negative at these single instances, in actual fact, effectively your voltage is as if your voltage is at somewhere around here, basically. So this AC voltage is almost the same thing as a DC voltage that is less in value. The heat that you derive from this heating element in joules, when you apply a 5 volts peak AC, it's like applying, you will get that same heat when you apply a DC voltage straight line of a lesser value, and that is called VRMS. That is called VRMS. So although we are in this way, we are seeing 5 to 5. In actual fact, I can replace this 5 volts to 5 volts AC with a DC of lesser value than 5 volts, and that value is VRMS. So what is VRMS? VRMS is V peak over root 2, or V peak multiplied by 0.7071. That's 1 over root 2 is 0.701. So we see that if our V peak, let's assume our V peak is 5 root 2, and this is minus 5 root 2 in volts, then our RMS value is 5 volts. 5 root 2 is higher than 5 volts. So basically, if you're applying 5 root 2 volts here as your V peak, it's as if you are applying 5 volts RMS. So I can replace a 5 root 2 waveform, AC waveform. I can replace this with a DC waveform of just 5 volts. I don't need to take my DC. I don't need this DC voltage to rise up to 5 root 2. If 5 root 2 is somewhere around here, I don't need to increase my DC voltage to 5 root 2. Ordinary 5 volts in DC will replace an AC that is going from 0 to 5 root 2 to negative 5 root 2 and back to 0. So the RMS value of an AC helps us know the equivalent DC that we can use to replace it. If you have an AC power source and you want to replace it with a DC power source, you need to know the RMS value. The RMS value tells us the equivalent DC, the equivalent DC power source or voltage source that you can use, especially if you want to use it for heating purposes. So with that, last semester we went through how to use the multimeter to measure voltage, and of course we know that you turn on your multimeter first. You have different voltage range of, let's take out the terminals. Here, if you look at these symbols, you have Hz frequency, Hz hertz frequency, you have V for voltage, and then you have this ohm symbol for your resistance. So if you want to measure resistance, you are using this terminal, and then this is common. It's common to all other terminals. So you basically put the black lead, the black terminal is your common, and then the positive terminal or the red terminal you either place on either of the three other terminals you have. So if you are measuring voltage, your common goes to black, and then the red goes to this voltage here because you have V. If it's resistance you want to measure, you place it here. If it's frequency you want to measure, you place it here. So if you are measuring current, that's amps or milliamps. If it's small current, this is microamps. If it's microamp you want to measure, you place it here. If you want to measure milliamps, you place it here. If you want to measure amperage, that's from 1 amp or from 0.1 amp up until maximum of 10 amps, you place it right here. So now we want to measure voltage, so you place it on terminals here. So this are knob to select different voltage readings of different electrical terms that we want to examine or measure. If you want to measure voltage here, now we have, I don't know if you can see this clearly, we have a straight line and another. This is so we can measure both DC and AC. Now if you use your terminal, you use your voltmeter, your multimeter to measure AC voltage. If you plug this into your public, two terminals into your public power supply, you are going to get something that looks like this. You're going to get 240 volts.